This diagram is a typical scenario that is often encountered in questions of rolling motion. A force F is applied at a perpendicular distance h from the center. So this is the center of the object that is rolling. This object is given to be rolling without slipping. So since it is rolling without slipping, naturally we can write down V is always going to be equal to R omega. And also if we do differentiate this equation, then we get another relation. Acceleration is going to be equal to R alpha. Alright. So the force F that is applied is parallel to the ground. So this force F is going to play an important role in the analysis of this particular question. Now there has to be friction. Without friction, it is not possible for this object to perform pure rolling motion. So let me assume that the friction at the point of contact is in the backward direction. In physics, we can assume directions of quantities like this without loss of generality, and if the friction happens to be not in the backward direction, then we'll get a negative value as per the equations. So we have not lost any generality in assuming that the friction is in the backward direction. This object is rolling without slipping. I am repeating, this object is rolling without slipping. So instantaneously this point is going to be stationary. Typically in such questions we are required to find the acceleration of the object, because see, the object is under the influence of forces in the horizontal direction, namely the force F and also the friction force. Also, the object is rotating angularly, and since the center of mass of the object would be translating and accelerating in the horizontal direction, the point of contact has to keep up because it is always rolling without slipping. That means it also has to accelerate angularly as per this particular relation. Now let us start the analysis. To start with, we can write down the force equation. The force equation is F minus F is equal to ma. Usually in such cases, the coefficient of friction mu is also given. However, this proves out to be redundant information because we do not know that the friction is going to be its maximum limiting value, which is mu n. So it is a mistake that most of the students do make to write the value of friction over here as mu mg, which is mu n. That is a mistake because the friction force is static in nature, because the point of contact is stationary instantaneously, and hence this force of friction F can take any value from 0. This force of friction F can take any value from 0 to mu n. This is very important to note. So F minus F is equal to ma is an equation that we have, and another equation is the torque equation. Now let us analyze what is the clockwise torque. So this force is acting at a perpendicular distance of h, so it will provide F into h. Sine 90 is 1, so we ignore sine 90. So F into h is the clockwise torque provided by this force F, and small f into r is also a clockwise torque provided about the center. So the net clockwise torque about the center, if I were to write, then I have to write down F into h plus small f into r. Now this net torque is going to be equal to I, the moment of inertia about the center, into alpha. So these are the three equations essentially that we have. Because of pure rolling, we get A is equal to R alpha. Now I'll just ignore this equation V is equal to R omega. Although it is true, it is not required because we are not supposed to usually find the velocity. We are here supposed to find the acceleration, the friction, and the angular acceleration. So these are the three equations 1, 2 and 3. 1, 2 and 3. Solving which we'll get the requisite quantities. Alright. So how to proceed in solving these equations? The best way to go about things is to eliminate the variables and reach a situation where we have a single variable and a single equation in order for us to be able to solve very easily. Now what I can do over here is I can multiply this equation with r. So fr minus small f into r will give me mar, and if I do that and add these two equations, this one and this one, if I add these two equations, then what do I get? I get fr plus fh is equal to mar plus I alpha. Now instead of writing alpha over here, I am writing a divided by r, because if I do this, then I'll get only a as the unknown. So this is I into a divided by r. So after doing this, we can understand that a is the only unknown left. If we simplify the right hand side, what do I get? I get a into bracket mr square plus I whole divided by r. This is what I get towards the right hand side. Alright, now this r can be shifted towards the left hand side. Therefore, I can write f into r square plus rh is equal to a into I plus mr square. So I can simplify and write a as being equal to f into r square plus rh upon I plus mr square. So this is a very important relation. This particular value of acceleration should be mugged up by the student. Usually I do not recommend the mugging up of formulae ad hoc per se, but this particular expression is very important in solving questions and hence can be remembered by heart. Alright, now let us continue our analysis, and if we were to find out the angular acceleration, it simply is equal to a divided by r. So no need to find out or mug that up basically. So if you just divide this by r, we get f into r plus h upon I plus mr square, that is going to be alpha. Now let's talk about, I'll just write down the expression of alpha over here. Alpha is going to be equal to a divided by r. So that is going to be equal to f into bracket r plus h upon I plus mr square. Simply. No need to remember this particular value of alpha. Now let us talk about finding the friction force. Now in this equation, friction force is simply going to be equal to capital F minus ma, and we already know a. So if we just perform this operation, capital F minus ma, let us see what we get. So friction force is going to be equal to capital F minus ma. So that is going to be equal to, let us get rid of this mu for a moment. Alright, so capital F minus ma is going to be equal to capital F minus m into capital F into r square plus rh upon I plus mr square. Now if we go ahead and simplify this, we get capital F is taken common outside, we get I plus mr square on taking the LCM minus mr square minus mrh whole divided by I plus mr square. So mrh is going to get cancelled, rather mr square is going to get cancelled from the numerator. Mrh will remain as it is, and we'll be left with the formula for the friction force, which I am going to write down over here. The force of friction F is going to be equal to capital F into bracket I minus mrh upon I plus mr square. So this is another expression that I would advise the student to remember by heart in order to solve questions involving forces applied on rolling objects where the objects are rolling without slipping. Now let us understand this equation a bit. So the friction force F is going to be positive if I is going to be greater than mrh. In that case, the friction force will always be in the backward direction, because backward is the assumed direction of the friction force in this question. Now if the height is 0, let us say in many cases the force is applied from the center. Now if the height is 0, then in that particular case or in that particular situation, what we can do is simply the fact that the friction force is simply Fi upon I plus mr square. So in that case also friction force will always be in the negative direction. If the height is negative, okay, so what does negative height mean? Negative height means that the force F is applied from a point that is below the center of mass. So let us say any point that is below the center of mass, the force F is applied at a negative height, because the height measured in the upward direction over here is going to be considered as positive, and measured downward is going to be considered as negative. So if the height is negative, still the friction force is positive. So essentially for small heights h basically, wherein mrh is going to be less than I, the friction is going to be in the backward direction. So you can roughly consider the range of friction to be backward if the force is being applied in this particular area. So what is this small height h below which the force has to be applied for the friction to be backward? It is very easy to find out. It is I divided by mr. So there is this particular height, let us say h naught. Let me consider this height as h naught. So h naught is equal to I divided by mr. This particular height h naught, if the force is applied anywhere below this height h naught, then in that case the friction is always going to be backward. And if the force is applied above this height h naught, then in that particular case the friction force can be forward as well, because what is going to happen is above this height h naught, I minus mrh is going to be negative. So since I minus mrh is negative, the assumed direction of friction will be wrong, and in that case the friction force will be in the forward direction if force is applied above the height h naught. Alright, this is easy enough to understand. Alright, now let us look at a question which is a very typical question based upon this concept. In studying that question, what I will do is I will erase out the analysis and just let the formulas of friction and acceleration persist in this particular page. And let us see how easily we can solve typical questions that arise. Now let us say there is an inclined plane. Let's say this is the inclined plane, This is a very typical question that comes up. Yeah. So this is the inclined plane, and let us say this is the angle theta of this wedge. Let's assume that there is a spherical cross-section object that is rolling down this inclined plane. Alright. So what is the force that is acting on this object? It is mg sine theta. Mg sine theta. Let us also assume that this object is undergoing pure rolling motion, which means that the point of contact is instantaneously stationary. Let us assume that the friction is in the backward direction. The friction force F is in the backward direction. Let us assume that this object is a sphere. Let us say it's a solid sphere. So moment of inertia is going to be equal to 2 by 5 mr square. Alright. So typically we are required to find the acceleration of such objects, and also sometimes the friction force acting on the object. So let us say we are asked to find the acceleration. The acceleration A is going to be equal to force. The force is what? Mg sine theta. I am directly using the formula that we have derived. This is a very commonly used formula. So this force F I have substituted to be mg sine theta into r square plus RH. Now this force is acting on the center, so there is no question of any height above the center, so this height above the center is 0. So mg sine theta into r square, so this is the numerator, divided by the denominator. The denominator happens to be, in this particular case, the denominator is going to be I, which is 2 by 5 mr square plus mr square. So typically this mr square gets cancelled and you get the answer after simplifying as 5 by 7 g sine theta. We can see that this answer is less than g sine theta because friction is present, and friction is trying to prevent slipping, and hence friction is trying to reduce the acceleration effectively from g sine theta to a lesser value, which comes out to be 5 by 7 g sine theta. Now let us say in this particular question I was not specified, let us say. Then what we would have to do is just write I over here. Instead of the expression for I, we just have to write down the value I. Then in that case, in many textbooks, this is a typical formula that is seen, but which is a very specific formula. It is g sine theta divided by I upon mr square plus 1. What we have done is a very general generic analysis that can be applied in many situations. So this is just a specific example of that particular situation. Alright, so please go through this particular video tutorial very calmly and understand everything properly. And these two formulae, unlike the norm, I am recommending that you mug up these two formulae because they are very crucially important, and they will definitely help in solving a lot of questions related to rotational motion and rolling motion, wherein a force is applied and pure rolling is taking place.